Good morning, everyone. Today, we are going to see radiation heat transfer, a unique process where heat is transferred via electromagnetic waves, requiring no medium like solid or fluids. Unlike conduction or convection, radiation can occur in a vacuum, making it critical for applications like solar energy and spacecraft thermal control. In this lecture, we will cover the fundamental laws of radiation, including the Stefan Boltzmann law, concepts like emissivity and absorptivity, and how radiation exchanges between the surfaces. We will also discuss radiation shields and practical applications in the engineering and technology. By the end, you will understand how radiation drives heat transfer to high temperature systems and natural phenomena. From the sun's warmth to the industrial furnaces, this process is essential for designing energy efficient systems and understanding the cosmic heat transfers. So let's start the principles of radiations and see how electromagnetic waves shape thermal energy transfer in the world around us. Let's start the basics of radiation heat transfer. Now, the radiation is the transfer of thermal energy through electromagnetic waves, primarily in the infrared spectrum, without needing a medium like air or water. This makes it distinct from the conduction, which requires direct contact, or convection, which involves the fluid motion. Radiation is significant in high temperature applications such as industrial furnaces, solar panels, and spacecraft, where other modes are less effective. For example, the sun heats the earth across the vacuum of space via radiation. All objects emit radiation based on their temperature, with other surfaces emitting more energy. This process is governed by fundamental laws we will explore, like the Stefan Boltzmann law. The radiation is crucial in engineering for designing systems that capture and manage radiant energy, such as solar connectors or thermal shields. Understanding radiation helps to optimize the energy efficiency and performance in extreme environments. So let's move to the basic laws that define how radiation works. Radiation heat transfer is governed by several key laws. The Stefan Boltzmann law states that the total radiant energy emitted by a surface is proportional to the fourth power of its absolute temperature, making temperature a dominant factor. Planck's law describes the spectral distribution of radiation, showing how energy is emitted across different wavelengths. Wind displacement law indicates that the peak wavelength of emission shifts inversely with the temperature. Hotter objects emit at a shorter wavelengths like visible light from a glowing filament. Kirchhoff's law states that good absorbers of radiation are also good emitters at the same wavelength, linking absorptivity and emissivity. These laws provide the foundations for analyzing radiation in the systems like the solar panels, where capturing a specific wavelength is crucial, or in furnaces where high temperature drive intense radiation. By understanding these principles, engineers can predict and control radiant heat transfer in various applications. So let's focus on the Stefan Boltzmann law next to quantify the emissions. The Stefan Boltzmann law is important in radiation heat transfer. It states that the radiant energy emitted per unit area, which is given by capital E, is equal to sigma into T raised to 4, where sigma is the Stefan Boltzmann constant. Its value is 5.67 into 10 raised to minus 8 watts per meter square Kelvin raised to 4, and where T is the absolute temperature in Kelvin. This means a small increase in the temperature causes a dramatic rise in the emitted energy due to the fourth power relationship. For a black body, an ideal surface that absorbs and emits perfectly, this law gives the maximum emissions. For example, a furnace wall at 1000 degree Kelvin emits significant more radiation than that one at the 500 Kelvin. The law is used to calculate the heat emissions from surfaces in applications like solar collector or industrial heater. In real systems, emissivity adjusts the equation to account for non-ideal surface. Understanding this law helps the engineer to design systems that manage high temperature radiations, ensuring efficient heat transfer or protection. Next, we will explore emissivity and absorptivity, which refine this model for the real surfaces. Emissivity and absorptivity are the critical properties in radiation heat transfer. Emissivity is the ratio of radiation emitted by a surface to that of a black body, which has value E is equal to 1. Now, the real surfaces like metals or the paints which have the value of emissivity between 0 to 1 depends on the material and its finish. Polished metals have low emissivity while dark surfaces have higher values. Absorptivity is the fraction of incident radiation absorbed by the surface, also ranging from 0 to 1. For a black body, the absorptivity is equal to 1, which indicates all absorbing radiations. Kirchhoff's law links these properties, stating that the emissivity is equal to absorptivity at the same wavelength for a surface in thermal equilibrium. For example, a solar panel with high absorptivity captures more sunlight but also emits more radiations if its emissivity is high. These properties are crucial for designing the surfaces in thermal systems like radiative coatings or insulations. By tailoring emissivity and absorptivity, engineers optimize heat transfer or minimize losses. So let's examine black bodies and real surface in the next session. Radiation exchange between the surface depends on the several factors: the emissivity, geometric orientation, and temperature difference. When two surfaces interact, like a hot furnace wall and a cooler object, each emits and absorbs radiation. The net heat transfer depends on their temperature, emissivities, and the view factors or the shape factors, which quantifies how much one surface sees the other. For example, the parallel plates exchange more radiation than the surfaces that are at angle. The net heat transfer rate between the two surfaces is calculated using the Stephan-Boltzmann law, adjusted for the emissivities and view factors. This is critical in systems like the heat exchanger, where radiation between the tubes must be accounted for, or in the buildings where the window exchange the radiations with the wall. Accurate modeling of radiation exchange ensures efficient thermal design, preventing overheating or the energy loss. By understanding these interactions, engineers can optimize the systems for specific thermal environments. So let's look at the radiation shields and insulation in the next slide. A black body is a theoretical model that perfectly absorbs all the incident radiations, whose value, that is absorptivity, is equal to 1, and emits the maximum possible radiation for its temperature, that is emissivity is equal to 1, and following the Stephan-Boltzmann's law. Real surfaces deviates from this idea. A gray body has a constant emissivity across all wavelengths, simplifying the analysis, but still emits less than that of a black body. Selective surfaces have emissivity and absorptivity that vary with wavelength. For solar panel designs to absorb sunlight but emit little infrared radiations. For any surface, the sum of the absorptivity, reflectivity, and transmissivity is equal to 1. Through transmissivity, it is often negligible for opaque surfaces. These distinctions are vital in applications like the thermal imaging, where the surface properties affects detections, or the spacecraft where selective surface manage heat. Understanding black body, gray, and selective surface helps the engineer to design materials that control the radiation effectively, balances emissions and absorptions. Next, we will explore the radiation exchange between these surfaces. Radiation shields and insulations are used to reduce unwanted radiation heat transfer. Radiation shields are highly reflective surfaces like polished metal with low emissivity and which is placed between the radiating surfaces to block or reflect radiation. For example, in a furnace, a shield reduces the heat loss to the surrounding and improving its efficiency. Multiple shields can further decrease the transfer as each reflects a portion of the radiation. Insulating materials like fiberglass or foam trap air to minimize the conduction and convection, but they also reduce radiation by scattering or absorbing infrared waves. In buildings, low emissivity coatings on windows reflect radiant heat, maintaining the indoor temperatures. In spacecraft, multi-layer insulation with reflective layer protect against solar radiations in space. These techniques are crucial for application requiring precise thermal control, such as industrial ovens or cryogenic systems. By using shields and insulations, engineers can significantly lower radiation losses, enhancing energy efficiency and system performance. Next, we will explore the practical applications of the radiation heat transfer. Radiation heat transfer has a wide-ranging applications in engineering and technology. Solar energy collection relies on radiation with panels designed to maximize absorptivity for sunlight while minimizing emissivity to reduce heat losses. Heat transfer in the furnace depends heavily on radiation due to high temperatures, where walls and material exchange radiant energy, requiring careful designs to optimize efficiency. Thermal imaging and infrared sensors use radiations to detect temperature differences applied in medical diagnostics, security, and environmental monitoring. Spacecraft thermal control systems manage the radiations to balance